Hello, I'm Alejandro Chamorro,
I'm Chris Milford. And I'm Eli Holt.
and this is our Project 1. So, for our project, we are looking at what is called the turntable. We are given a mass of a block, pulley system, a turntable, and a hollow sphere, all connected on a string. Now, in this scenario, we have the turntable spinning, and we also have the hollow sphere unwinding as it's traveling down. Now, by looking at this is going to give us a pretty unique property that we're going to see later in our equations. But we have to think that as this table is spinning and as it's flowing down, this ball is also spinning in that direction with the table. Now let's go ahead and look at the free body diagrams. We're first going to analyze the block. On the block, we have a normal force and the force of gravity, and those are equal to each other. We also have the force of tension. Now in this, we also know that the net force of tension is all going to be in this positive x direction if we set our coordinates to x positive. Now for the spool, or for the hollow sphere, we also have force of gravity acting, and we have force of tension going up. And at the same time, as seen from our previous part, we have an angular acceleration. Now, we're going to go ahead and break this problem up piece by piece. And before we can do that, we have to have some type of assumptions that we're dealing with in this problem. First, we're assuming that we have an ideal string, so there's no tension when the string is being having these forces applied to it. We have a frictionless surface. We have a uniform mass, so all the mass throughout the block and the sphere is equal. And we have an ideal massless pulley, since we're assuming that the pulley has no mass on it and is working just as it should. So let's go ahead and look into the solution to this problem.
The symbols we're going to be using in this project are, for the block, we're going to use mass M and centripetal acceleration A, which is currently unknown to us. For the turntable, we have symbols R for the radius, I for the moment of inertia of the turntable as it spins, and omega for the angular speed, which is also unknown. For the ball, the symbols we have are little m for mass, little r for the ball's radius or the sphere's radius, I for the moment of inertia of the ball as it spins, the force of tension in the string that's holding up the ball, which is currently unknown, and the torque put on the ball, which is also currently unknown. Some of the equations that we'll be using over here are the equation for centripetal acceleration, Newton's second law, Newton's second law of rotation, conversions between tangential and angular velocities and acceleration, the equation torque equals force times radius, and the equation for net force equaling the force of gravity minus the force of tension, specifically for the ball. Now we're going to calculate the angular speed of the turntable. So the first thing we want to do is symbolically find the angular speed with the symbols that we have. So first we're going to use Newton's second law, F equals ma, for the tension in the string. Then we're going to convert this centripetal acceleration to v squared over r using one of our equations, and then convert that v squared into omega squared r squared. Then cancel out the extra r's that we have and solve for omega squared. And then root the entire equation, and we get omega equals square root the force of tension over large mass times the radius. Then we have to find the moment of inertia of the ball. So first we have the moment of inertia of the ball spinning in the vertical direction as it unwinds, which is 2/3 mr squared for a hollow sphere. Then we have the moment of inertia for the turntable, which is mr squared. And if you add them together, we get 5/3 mr squared. This is the inertia we'll be using moving forward. Or the moment of inertia we'll be using moving forward. Next, we're going to find the force of tension. So we start with Newton's second law of rotation, which is torque equals moment of inertia times angular acceleration. This torque can be replaced with the force of tension times r, radius of the ball. And then we can move the radius to the other side. We can convert the angular acceleration to centripetal acceleration over r. And then we can substitute in our equation we got over here for moment of inertia into our equation and cancel out any extra r's we had. And finally, that leaves us with the force of tension equals 5/3 mass of the ball times centripetal acceleration. We still don't know centripetal acceleration now, so we need to come back here and solve for it. So we use the net force on the ball, which is force of gravity minus the force of tension. We expand these out to use mass and acceleration, and mass times gravity for the force of gravity. And then we can substitute in our equation for the force of tension up here and for the force of tension here. And that gives us a whole bunch of m's that we don't want. So we can cancel out those m's. And that leaves us with the centripetal acceleration equals the acceleration due to gravity minus 5/3 the centripetal acceleration. If we simplify and solve for the centripetal acceleration, that gives us 3/8 gravity. We can then plug that back in to try and find the force of tension in terms of gravity, which we know, rather than the centripetal acceleration, which we've done. So if we take Newton's second law of rotation again, replace it with force of tension times radius, cancel a bunch of r's again, and it leaves us with the force of tension equals 5/3 mass of the ball times 3/8 for acceleration due to gravity. And if you multiply this together, you get 5/8 mass gravity. So then we can finally take this force of tension that we solved for with known quantities and plug it back into our initial equation of angular speed, and that gives us angular speed of the turntable equals the square root of 5 times mass of the ball times gravity over 8 times mass of the block times the radius of the turntable.
Alright, so now we're in the part of the project where we need to talk about our sense making. To start off first with our sense making, we first need to do our units check. So we figured out what the equation for our angular speed was. And we know that the units for this are going to be radians per second. We also need to figure out what the units are going to be for each one of these. So we know the mass of the ball is going to be kilograms. We know that the acceleration of gravity is going to be meters divided by seconds squared. And then we know the mass of the block is also going to be in kilograms. And of course, r, the length of the radius, is going to be in meters. So if we plug in the units into our equation, we get mass times gravity divided by mass times the radius. So that's kilograms times meters per second squared divided by kilograms per meter. And this is all over or under the square root, I should say. So if we cross out kilograms here, we get meters divided by seconds squared divided by m. And then we need to cross out our m's. So we now have no m's, it's just seconds divided by nothing squared. And we have that in the square root. We can cross out the square root and we can cross out the squared right there, which will give us radians per seconds. The reason why we switch from meters to radians, even though we lose out on meters, is because radians is technically unitless. All right, so now it's time to plug in our equation. So to start off with the mass of the big block, we're going to have it at 1 kilogram. For the mass of the small block, we're going to have it at half a kilogram. The acceleration of gravity is always going to be 9.8 meters per second squared. And then for a radius, we chose it to be 1 meter. We plug that into our equation. That will be 5 times 1/2 times 9.8 divided by 8 times 1 times 1. That just gives us divided by 8. We did all this on our calculator, which gave us 1.75 radians per second. Basically, this means that every second, the turntable will spin around 1.7 times. All All right, and then we're gonna go over here and make physical and logical sense of this. So right here, we have our graph that shows the angular speed in relation to the mass or the radius of the object. If we have this equation right here and everything is a constant besides the mass of the large block, we will know that the limit as it approaches infinity will be 0. And then because these are multiplied by each other, it's the same exact graph. So the limit will also be 0 as it approaches infinity. And then as the limit approaches 0 for r and m, it's going to be infinity once more. Now, the graph where the angular speed is in relation to the mass of the small block, we know that there's only one thing here, so we can't multiply. It's not going to be the same graph. If everything else is a constant, we know that as m approaches infinity, we'll get infinity as our limit, and then as m approaches 0, our limit will be 0.
The other problem that we thought related to this project the most was this problem from Studio 4. It was activity 2. In this problem, we had 2 hanging masses from a pulley, a massless ideal pulley. And the mass on the left did not rotate at all, it just fell straight down. And the mass on the right was a spool, so it unspooled as it fell down. This problem has, the similarities between this problem and our project are between the spool on the right here and the ball that's unwinding as it's falling down in the center of the turntable. They both use the same principles of using torque to help find the tension to end up figuring out the acceleration of either of the masses.